This tutorial demonstrates a 4-bar linkage analysis using SimXpert Motions workspace. The objective of this tutorial is to perform a dynamic analysis of a 4-bar linkage using rigid parts and then replacing one rigid part with a flexible part, thus showing how both the SimXpert Motion and Structures workspace can be used on one model. In this tutorial, we will simulate the motion of a 4-bar linkage, mainly focusing on Motions workspace in SimXpert, which allows us to create and run kinematic or dynamic simulations to see how different parts interact relative with one another. There are different types of entities that can be created in the Motions workspace, such as parts, connectors, motion drivers, etc. We can also create connections between parts to define how they are constrained relative to one another. We can also define contacts between parts, impose motions on connections, and also apply forces to drive the systems. In SimXpert, make sure that you are in the Motions workspace. For this tutorial, we will use millimeters and newtons. Then select CAD import. Make sure that the Create a part for each body is checked. Otherwise, all bodies inside the Parasolid file will be assigned as one part in our model. Import the Parasolid file containing the linked bodies. Now create motion part for each link. We do this step to control which bodies from our CAD file are assigned to which part in our model. Each motion part can be created individually, or all parts can be created in one step. Here we have decided to offer the combined approaches. To manually create the part, navigate to Components in the Tools menu bar, select Part, and enter Link 1 for the name. Check the geometry on the source of inertia and select Part 1 from the model browser on the geometry text box, then click OK. Still under the Components, navigate to From Geometry under the Advanced group. All the imported CAD bodies are now listed here, from where we can select the part to create, as well as which bodies to assign to ground. Notice we do not have to create part 1 again. Rename part 2, part 3, part 4, part 5 as link 2, link 3, lag 1 and lag 2 respectively. Check the last two boxes under the ground part. Ground part are indefinitely fixed and are excluded from the analysis. Their only function is to attach the other parts to the ground at certain locations. Now create motion connections to define the type of connection between the parts. Click on Connections in the Tools menu bar, select Revolute, click on the definition in the form. Under Part 1, select Link 1 and Link 2 under Part 2. Select Geometry on the Location 1 method text box, and under Feature, select Edges in the picking filter, and select the circular edge for the hole that connects Link 1 and Link 2 in the model window. To make this selection easier, we will zoom in to make this selection, then click Apply. This procedure defines how and where Link 1 and Link 2 are connected, how they are allowed to move relative to one another. Now, we can see the graphics for a revolute joint and check that it is orientated to allow the correct rotational direction. Our orientation is global in our connection creations, so that the z-axis points in our preferred direction. Repeat this procedure to create revolute connections between link 2 and link 3, link 3 and lag 2, and finally link 1 and lag 1. Using curves to locate joints, we will ensure the point is placed on the arc center. Click OK instead of Apply on the last connector's definition to simultaneously apply and close the form. Now we will create a motion on one of these connections. Navigate to Motions in the Tools menu bar and click on Joint Motion. Select Connector 1 under Joint Name and change the motion type to Velocity, meaning that we are imposing a velocity motions type. Type in 90D, which means a velocity of 90 degrees per second is applied to the first joint. Click OK when finished. Next, run the simulation. Click on Simulation in the Tools menu bar. Select Simulation. Name it Rigid Link. Set the end time to 4 seconds and steps to 200. Checking the control boxes are optional, but it is important to select both the Keep Result in memory and hide when finished. Then click on Begin Model Simulation icon. You may also choose to view the animations. Navigate to Results, select Animation, then click Play. Now we can see how these parts interact with one another. We can speed up the animations by selecting any individual time step or moving the speed bar. Now we will prepare to replace one of the rigid link with its flexible version, which we will create using finite elements. We need to define which nodes of the finite element's body will be used to transfer the connection loads. Since we do not have nodes yet, we will use the geometry faces to define the load transfer areas. Any nodes created later on these faces will be rigidly connected to a center node at the center of the joint. Rotate the 4-bar linkage as shown, then click on Link 2 in the model browser to open the Properties editor. Navigate to Loads, then click in the Load Bearing Geometry field for Connector 1. Select Edges in the picking filter. Zoom into Connector 1 and select the cylindrical surface inside the link nearest to Connector 1. Click Apply and select the Load Bearing Geometry text box for Connector 2. Then select the inside surface inside link nearest to Connector 2 and click Apply. We can now control how finite element body should be created without needing to manually switch to Structures workspace. Having navigated to the Structures tab, enter a value of 210,000 megapascals for the Young modulus and 0.3 for the Poisson's ratio. The density is already defined under the parts properties. Make sure that the Create New and Use Defined are selected. Enter an element size of 7 mm and 10 for the number of modes. Now we can create the automate process to create the flexible parts and replace the rigid part. Check the automate text box, click Apply, then click on Create Flexible Part button. Notice that during this process, SimXpert will switch to the Structures workspace, define the structural analysis properties, submit the analysis job, load the nesting results, switch back to the workspace, and replace the rigid link with the flexible link. If you are not satisfied with the result, you may repeat the process by changing the input parameters or even uncheck the Automate text box to manually create the flexible part in the Structures workspace. Notice that even with the Automate text box unchecked, SimXpert will set up the appropriate job analysis. After manipulating the mesh, we will only need to run the analysis for it to complete the switch back to the Motions workspace, where you will reference the results under Flexible Body. Now run a new simulation. Name it Flexible Link, give it a time duration of 4 seconds and 200 steps. Keep the result in the memory, hide when finished, then begin the model simulation. The dialog box should close itself when finished solving. Double-click on Animation in the model browser, a step that can be bypassed by clicking on Result in the Tools menu bar and selecting Animation. Select Flexible Link. Run under Result, Set, and Play. Adjust the speed if necessary. Now we are able to display the stress result on the flexible body. Click on Plot Data tab, select Stress under Result tab and von Mises under Derivation. Click on the Deform tab still under the Animation form and set Display to No Edges. Notice that this step increases the animation speed and makes it easier to see the contours when zoomed in. Go back to the Animations tab, click Play to view the changes made. Can you see the fringe plot? Notice the stress values and also that the link can only experience actual forces due to our setup. Now let's include a spring to our model to induce bending on our flexible part. Click on Force in the Tools menu bar and select Rotational. We would like to put the spring between link 3 and log 2 because in real life the model is always preloaded. Choose the geometry method to specify location 1. In the Features text box, select Edges in the picking filter and select the edge of the hole it lugged to, thus locating the rotational spring at the arc center. Select Global under Orientation Method, check the stiffness box, define your stiffness rate. No damping is required. Then click OK. Notice the change in the model window. Next, perform a new simulation, name it Spring Link. The simulation parameters should default to the previous run, so no need to change them. Begin model simulation, then animate the result when the run is completed to view the fringe plot of the link stress with the spring included. Notice the increase in stress and change in stress pattern since the link now experiences bending due to the added rotational spring. We now want to view the result in the graph form. Click on Chart under the Result tab in the Tools menu bar. Under Dependent Data tab, hold down the Control key and select both the Spring Link Run and Rigid Link Run, and select Link 1 under Entity. Select X for the quantity, then click Add Curves. This procedure superimposes the two selected simulations, now visible under the chart result. Spend some time on this chart to be able to interpret the graphs. This concludes the tutorial on how to analyze dynamic system and introduce flexible parts. This tutorial was brought to you by ESTEC, Engineering Technology for Better Business.